Welcome to this explainer, where we're going to completely shatter a massive misconception about back-end infrastructure. You know, so many engineers operate under this assumption that databases write their data directly to the disk immediately upon an insert or an update. Well, today, we're breaking down the reality of how databases actually handle write operations. And as you'll see, designing a system with that assumption would actually be a complete disaster.
Now, right out of the gate, you're probably asking yourself, wait a minute, if databases aren't writing my data to the disk right away, how on earth do they ensure durability without losing everything the second the power goes out? I mean, that's the whole point of a database, right? Well, the answer is a pretty fascinating piece of engineering.
Okay, so here's our roadmap for uncovering this back-end magic. First, the direct write myth. Second, why disks are expensive. Third, the memory and log strategy. Fourth, enter the check pointer. Fifth, hidden benefits of logs. And finally, pro-optimization tips. Let's dive in.
Section 1. The direct write myth, shattering our assumptions.
It really all comes down to the fundamental architecture of computers. Writing data to a storage device is computationally expensive, mainly because the storage is a peripheral device. This means it lives entirely outside your immediate compute resources and requires some seriously heavy I/O operations. It honestly doesn't matter if the storage device is directly connected as a storage block, like say Amazon EBS connecting directly to your EC2 instance, or actually, even if it's a separate compute resource you communicate with over a network, like Amazon EFS. Regardless of the setup, disk I/O is always expensive because you're crossing outside of your immediate compute domain.
Moving on to Section 2. Why disks are expensive. The hardware problem.
Depending on your hardware, immediate writes can be a literal system killer. If you're using traditional disks, yeah, they're highly durable, but they're painfully slow when it comes to random write operations. Now, you might be thinking, hey, I use SSDs, so I'm totally fine. But SSDs have a completely different, very severe problem: wear-out issues. Because of how SSDs are physically designed, if you update something, it has to wipe out the existing area and rewrite it in an entirely different spot. Because of this constant wiping and rewriting, if your write rate is too high, your SSD will literally wear out and eventually become completely useless. This is exactly why it's a common practice in system design to avoid disk writes as much as humanly possible.
Which brings us to Section 3. The memory and log strategy. The real heroes.
So if direct writes destroy hardware and cause massive latency, how do databases actually handle updates durably? Well, here is where the magic happens. Instead of heavy data writes, the database engine does something absolutely brilliant. When you execute an insert, the database writes the actual data into fast memory, and then it simply saves a lightweight log of the change to the disk. Writing a sequential log is vastly more efficient than writing the entire data block. Think about updating a specific column in a row. The database engine can't practically just go into the disk and neatly alter a single column. It usually needs to read the data, alter it, and save it back, or write a whole new version of it entirely, kind of like what happens in Postgres' MVCC architecture. All of those disk I/O operations are incredibly costly. But if you just keep a lightweight log of the change on the disk, it's a significantly smaller workload than rewriting the data itself. Next up, Section 4. Enter the check pointer, the unsung janitor.
But hey, memory capacity is limited, right? So we need a way to safely clear it out. Enter the check pointer. It acts like a background sweeper that periodically cleans up those filled memory spaces by taking the data and finally writing it into the disk in one efficient bulk batch. This clears up the memory to grasp more data for new write operations. If you ever actually look at your Postgres logs, you can see the footprints of the check pointer doing its job. And here's the best part. Apart from just running on a schedule, the check pointer is also triggered if the memory gets completely filled and can't handle new writes, basically stepping in as the ultimate savior of the day to prevent your whole system from crashing.
So, the crucial takeaway here is this really elegant two-step dance. Step 1, the query executor handles the immediate request, interacting with the lightning-fast memory and just writing that lightweight log to the disk for durability. Step 2, behind the scenes, the check pointer does the heavy lifting, cleaning the memory and saving the actual bulk data to the disk on its own time.
All right, Section 5. Hidden benefits of logs. Beyond basic writes. These logs aren't just for speed. They're actually solving other massive systemic problems. First off, they allow the database to ensure strong consistency in a transaction. Let's say a transaction only partially executes and something goes wrong. The database uses these exact logs to revert those changes, keeping your data perfectly pristine. Plus, they're the absolute secret to efficient replica syncing.
In system design, relying on a single database instance is a huge single point of failure. So we use multiple instances, called replicas, to distribute the read and write workloads. Now, these replicas need to stay synced, right? If we had to send the entire actual dataset over the network every time a single change happened, it would consume massive amounts of bandwidth. Instead, we just send those lightweight logs. It's a total game changer.
And finally, Section 6, Pro Optimization Tips. Applying the reality.
Okay, here is where this turns into pure gold for optimizing your own setups. Since we now know the database relies on memory, we know that less memory equals slower write speeds. Why? Because a small memory cache fills up way too fast, which triggers that checkpointer right in the middle of your peak write operations, and that introduces massive latency. For example, if you're using Postgres, it uses a tiny 128 megabyte memory cache by default. Since Postgres is already infamous for write amplification due to its MVCC architecture, you should absolutely bump up that memory allocation to help handle your peak workloads. And if you use MongoDB, listen to this, because there's a massive catch. Everything we just talked about, saving a log instead of writing directly to disk, does not happen by default in Mongo. You actually have to enable the replica set configuration. Yes, even if you are literally only running a single instance of MongoDB, you must enable replica set so it actually utilizes oplogs. If you don't do this, MongoDB is going to write data directly to the disk, completely bypassing all the optimizations we've just talked about.
So I'll leave you with this final thought to challenge how you allocate resources in your next architecture build. If your system's speed and hardware survival dictate that data absolutely has to hit memory first, are you artificially bottlenecking your own performance by starving your database of RAM? Take a look at your caching configs, check those replica set settings, and give your databases the breathing room they actually need to do their jobs efficiently. Thank you so much for joining this explainer, and I really hope this transforms how you design your next backend system.